Math 2414, area between curves. Now that we're finished learning integration techniques, including evaluating improper integrals, we're going to start a series of videos, a series of series, discussing the applications of integration, or rather further applications of integration. You might remember that the genesis of integration was calculating the area under a curve, namely by finding a Riemann sum, which is a fancy way of saying, let's cut it up into a bunch of rectangles, calculate an expression for the area, and then take a limit as the widths of those rectangles approach zero. And then boom, calculus happens and we get the integral, the definite integral, that calculated the area under a curve. The first application that we're going to investigate in this series of videos is how to find the area between two curves. And this might be so intuitive that you can figure it out without me walking you down that path. So I've got a setup here where we've got one function on top of another. In other words, we have f of x is greater than or equal to g of x on the interval a to b. So between here and here, the graph of f is above the graph of g. They could coincide at a point because of the or equal to, but the f is never below the g. And our objective is to figure out, how do we find the area between these? Well, we could take a Riemann sum approach where we cut this into some rectangles and find an expression for the area of that rectangle, and then do the Riemann sum, take a limit, and boom, we have an integral. But let's use what we already know. We already know that when you integrate a function over an interval, you get the net area between that function's graph and the x-axis. And specifically, if the function is above the x-axis, then the definite integral tells us the area below. For example, if we were to calculate, we'll call this red area area 1, that's what we're looking for. But if we wanted to calculate area 2, well, that is just the area underneath the graph of g of x between a and b. And that would just be the definite integral from a to b of g of x dx. So can we do the same thing for f and calculate the red area? Well, not entirely. Because if we did the same thing with f instead of g, it would give us the total area, the red plus the blue. And I think some of you can see where we're going here. If we did the integral from a to b of f of x dx, that would give us the red area plus, so area 1, plus the blue area, area 2. Because together, those make up the entire area underneath the graph of y equals f of x. But what we want to know is what the red area equals, so we can just subtract this area from both sides. And we can come up with that the red area is going to be the integral from a to b of f of x dx minus the blue area. I don't know why I keep putting these caps on. But where did the blue area come from? The blue area came from doing the definite integral for g. So our red area is the integral from a to b of f of x dx minus the same thing for g. Integral from a to b of g of x dx. But because of the linear nature of the integral operator, we can combine this into a single integral and say the integral from a to b of f of x minus g of x dx. And that is our setup to calculate the area between. So, we can say the following. If f of x is greater than or equal to g of x on the interval a to b, comma, then the area between g of x and f of x on this interval, so on a to b, is the integral from a to b of f of x minus g of x dx. And I don't think it's that hard to see that. It's just the total area, the area between is the total area minus the unwanted area. Now you do have to be careful because there's a few things that could go wrong, as we're going to see in some of these examples. For example, this whole premise about adding and subtracting areas was based on the assumption that everything was above the x-axis. If anything dips below the x-axis or is completely below the x-axis, or they're all below the x-axis, the process would still actually work. And the reason is really simple to explain. Let's pretend for a moment that these guys were the same, except they were shifted down to where they dip below. Well, there would probably be a finite distance below which they were below the x-axis, like maybe they're 2 units or 3 units or 10 units below the x-axis. If we knew how far down they were below the x-axis, we could add that to each function, so we'll say plus k, where k is the distance below the x-axis, and that plus k would move them all up. But it wouldn't change the area between them. When we subtracted these functions, the k's would cancel and we would get back to this anyway. So it really doesn't matter if our functions are above or below the x-axis. All that matters is that one is above the other. What if they overlap? Well, we'll cross that bridge when we get to it. All right, so yeah, this is what we're going to be doing for the rest of this series.